Welcome to this session on neural network training in PyTorch. Up to this point, we've explored the foundations of neural networks, what they are, how they're structured, and how concepts like tensors and automatic differentiation support learning. In this session, we bring those ideas together and focus on how a neural network is actually trained using PyTorch. We'll look at the essential components of the training pipeline: preparing data, defining a model with the torch.nn.Module, choosing a loss function and an optimizer, and understanding how gradients update the model's parameters. You'll see how these pieces work together inside the training loop that allows a network to learn from data. By the end of this lecture, you'll have a clear picture of how neural network training operates in practice and how to implement it step by step in PyTorch, preparing you for building complete models and applying them to real tasks. In this slide, we're looking at the complete pipeline for training a neural network in PyTorch. Every model you train, whether it's a simple linear classifier or a deep convolutional network, follows this same sequence of steps. We always begin with data, preparing and loading it in a format the model can use. Next, we define the model using PyTorch's torch.nn.Module. Once the model structure is ready, we choose a loss function, which measures how far the model's predictions are from the correct answers. We then select an optimizer, which determines how the model's weights are updated during learning. With these components in place, we run the training loop, where the model performs forward passes, computes loss, backpropagates gradients, and updates its parameters. Finally, after training, we move on to evaluation, measuring the model's performance on unseen data. This pipeline forms the backbone of neural network training, and the upcoming slides will walk through each part in more detail. Before a neural network can learn anything, it needs data, and how we prepare that data has a direct impact on model performance. Neural networks learn patterns by seeing many examples, so the first step is organizing those examples into a dataset. A dataset stores both the input features and the corresponding labels the model should predict. In PyTorch, we typically use a DataLoader to handle batching, shuffling, and efficient loading of data during training. Batching helps the model learn from small groups of samples at a time, which improves both efficiency and stability. There are also a few common pre-processing steps. We usually normalize or scale the input values so that all features are on a similar range. We convert raw data into tensors, since PyTorch models operate on tensor structures. And finally, we split the dataset into training and evaluation sets so we can check how well the model generalizes. At the bottom of the slide, you can see the overall flow. We start with a dataset, load it with a DataLoader, break it into batches, and then feed those batches into our model for training. In PyTorch, neural networks are built by creating your own model class. To do that, use subclass nn.Module, which is the base class for all neural network components in PyTorch. Inside the dunder_init function, you define the layers you want the network to use. In this example, the model has three components: a fully connected layer called Layer 1, a ReLU activation function, and a final output layer. These layers don't do anything yet. You're simply setting up the structure of the network. Next, the forward method defines how data flows through those layers. When you pass input X to the model, it first goes through Layer 1, then the ReLU activation is applied, and finally it passes through the output layer to produce predictions. It's important to remember that you never call forward method directly. Instead, you call the model like a function, for example, model of X, and PyTorch will automatically run the forward method for you. This pattern of defining layers in dunder-init and computations in forward method is the foundation of almost every PyTorch neural network you'll build. In PyTorch, most neural networks are built using predefined layers from the torch.nn.Module. One of the most common layers is nn.Linear, which represents a fully connected layer. Another widely used layer is nn.Convolution 2D, which is the core building block of convolutional neural networks for image processing. To introduce nonlinearity into the model, we use activation functions. Some of the most common ones include ReLU, pronounced ReLU, sigmoid, which squashes values between 0 and 1, and hyperbolic tangent, or tanh, which outputs values between -1 and 1. PyTorch also gives us a convenient way to chain layers together using nn.Sequential. With Sequential, we can define a model by listing layers in order. For example, a linear layer, followed by ReLU, and then another linear layer. This automatically builds the forward pass for us in a clean and readable way. Understanding these layers and activations gives you the building blocks to design a wide range of neural network architectures. When we train a neural network, we need a way to measure how well the model is performing. That's the job of the loss function. The loss tells us how far the model's predictions are from the correct target values. And lower loss means the model is doing better. PyTorch provides several commonly used loss functions, each designed for a different type of task. For classification problems, such as recognizing digits or detecting objects, we typically use nn.CrossEntropyLoss, which works with multiple classes and compares predicted probabilities with the correct labels. For regression problems, where the model predicts continuous values like prices or temperatures, we use nn.MSELoss, which stands for mean squared error. And for binary classification, where the output is yes or no, true or false, or 0 or 1, we often use nn.BCELoss, or its more numerically stable version, nn.BCE with logits loss. At the bottom of the slide, you can see a simple example. Criterion equals nn.CrossEntropyLoss. This line initializes the loss function, and we'll use it during training to compute the loss for each batch. When training a neural network, we need a way to update the model's weights based on the gradients computed during backpropagation. This is the role of an optimizer. The optimizer decides how much and in what direction each weight should change in order to reduce the loss. PyTorch provides several built-in optimizers in the torch.optim.Module. Two of the most commonly used ones are SGD, or stochastic gradient descent, a simple method that updates weights using a fixed learning rate. Adam, short for adaptive moment estimation, a more advanced optimizer that adapts the learning rate for each parameter. Because of its stability and good performance, Adam is often the default choice for many models. To create an optimizer in PyTorch, we pass in the model's parameters along with a learning rate. For example, optimizer equals torch.optim.Adam, with model.parameters and learning rate set to 0.001. This optimizer will be responsible for adjusting the weights during training, as the model learns from the data. Now that we have a model, a loss function, and an optimizer, the next step is actually training the neural network. In PyTorch, training follows a very consistent pattern, and you'll see this same structure across almost every project. The process begins with a forward pass, where we feed a batch of data into the model and compute predictions. Next, we compute the loss by comparing those predictions with the target labels. Before we compute new gradients, we must zero out any existing gradients using optimizer.zeroGrade. This step is important because PyTorch accumulates gradients by default. Then we perform the backward pass by calling loss.backward. This is where PyTorch applies automatic differentiation and computes gradients for every weight in the network. Finally, we call optimizer.step to update the model's weights based on those gradients. The code example at the bottom shows the full structure. We iterate over the training DataLoader, compute the forward pass, compute the loss, clear old gradients, run back propagation, and update the weights. This cycle repeats for every batch and for multiple epochs, gradually improving the model's performance. Now that we've covered how to train a neural network, the next step is evaluating its performance. Evaluation works a bit differently from training because we don't want the model to update its weights or track gradients during this phase. First, we switch the model into evaluation mode by calling model.eval. This tells certain layers, like dropout or batch normalization, to behave differently compared to training. Next, we wrap the evaluation loop inside torch.nograd. This disables gradient tracking entirely, making evaluation faster and more memory efficient. Inside the loop, we simply pass the input data through the model using model of data, collect the outputs, and compute whatever metrics we care about, such as accuracy, precision, recall, or loss on the test set. The key idea is training requires gradients, but evaluation does not. So evaluation mode plus nograd gives us a correct and efficient way to measure how well our model is performing. After training a neural network, we typically save the model so we can reuse it later without retraining. In PyTorch, the standard practice is to save only the model's state dictionary, which contains all learnable parameters such as weights and biases. To save the model, we use the torch.save function. This function takes two inputs: the model's state dictionary, obtained with model.stateDict, a file name, for example, model.pth, which specifies where the weights will be stored. This creates a file on disk containing the trained parameters. To load the model later, we first read the saved file using torch.load, and then pass the loaded weights into the model's load_stateDict function. In other words, you can load the saved weights by calling the torch.load function and giving it the file name model.pth. This returns the state dictionary that was stored on disk. Model.load_stateDict copies those weights back into the model. After loading, the model is fully restored and ready to run predictions just as it did after training. Before we wrap up, here are the key points to remember. Training a neural network in PyTorch follows a clear workflow. You define the model architecture, choose the right loss function and optimizer, run the training loop to update weights, evaluate the model without computing gradients, and finally, save your model so you can use it later. These steps form the foundation for training almost any deep learning model. If you have any questions about any part of this workflow, from building the model, to running the training loop, to saving and loading your results, please feel free to ask. I'm happy to help clarify or review anything in more detail.